It's my great pleasure to introduce you Jaydeb Sarkar from Indian Statistical Institute at Bangalore. And he's going to talk about commutant lifting and Nevanlinna-Pick interpolation in several variables. Jaydeb, please.
Thanks, Javad, and thanks for the opportunity, Javad specifically. So we'll talk about lifting and Nevanlinna-Pick interpolation in several variables, as the title suggests. And oops, how it goes. It is.
Sometimes double click and it works.
Oh, okay. Yeah. Oops. All right. So this is a joint work with Deepak, another Deepak. First one is PhD student, second Deepak is postdoc, and Dan Demotin is a very well-known expert of this field. And this is a paper appeared in last year, 2020. So first of all, I do not know the range of the audience, so I'll try to keep it simple and easygoing. Give you some review and all that, and give you some of the proofs. So here are a couple of notations: H, E, and E star. I'll say E and E star, etc. will be Hilbert spaces, and they're always separable and over C. Linear operators will be assumed to be bounded, and this is the notation. This is Dn, the n polydisc, and this is the notation for elements in Cn. Subsequently, this is Bn, the open unit ball, and here is your H infinity of omega. Well, or for us, omega will be either Bn or Dn. And this is the favorite Banach algebra, and of course, we talk about several variables. Perhaps we will not have a chance to talk about one variable, but even if you want to talk about H infinity of D, that's a very, very wide object, and lots of important questions are still open. However, we'll talk about several variables. And number 6 is the Schur class. So look at all those functions which are bounded by 1 from H infinity of omega. P sub S, whenever S is a closed subspace of a Hilbert space H, will denote orthogonal projection onto S. And I sub S is the inclusion. As usual, S is a closed subspace of H. And RKHS will be the short notation for reproducing kernel Hilbert spaces. And here is our roadmap for today. So we'll talk about, first we'll talk about the classical Nevanlinna-Pick interpolation, then Sarason's commutant lifting, then move to dilation, take a halt on at the bidisc. Of course, bidisc is not the focus of this talk, but I think it is not right to not touch Agler result while you talk about interpolation. Then we'll talk about several variable lifting in our setting, and then some factorizations, and finally Nevanlinna-Pick interpolation on the ball. All right, so this is the classical Nevanlinna-Pick interpolation. So Nevanlinna did it in 1919 and Pick in 1916, perhaps during the time of First World War. So you have distinct P points Zi in D and P points Wi. Omega, okay, Wi in D. So given that, there exists a Schur function, that means H infinity function, but the norm is less than or equals to 1, such that this interpolates Zi goes to Wi for all I, if and only this P by P Pick matrix is positive. So this is a okay. So this is a P by P matrix, and this relies only on your data. So Wi and Zi. Okay. In other words, given this Zi and Wi, you are asking existence of phi such that phi Zi equals to Wi, and then you are saying this happens if and only this so-called peak matrix is positive definitely. So now let's talk about interpolation and Sarason. So this is the picture you just saw in the previous slide, And if you look at it this carefully, so this is a question in complex analysis. You can always ask this question, the complex analysis class, for instance. And the right-hand side, this one is positivity. So this is a question about linear algebra. And often it is, of course, it is quite checkable. And then Sarason came and he introduced what we call as commutant lifting theorem, and that's pretty much operator theory. And Sarason's commutant lifting theorem gives you this equivalence, and so it's seemingly different subject. It's got get connected through Sarason's commutant lifting theorem, and that also one of the reasons that's a very important and deep result, which we'll explain again. From this point of view, I recommend you to look at, of course, there are many books, but this article by John is very interesting, and it appeared in 2003. It's very nicely written. So have a look at it. All right, so to introduce Sarason's commutant lifting, I have to talk about Hardy space. Of course, been already talked about by Michael, but let me do it one more time. So again, the D is a disk, and H2D is the set of all holomorphic function on the disk, for which, so you look at the power series, and the power series should be square solvable. And that's your H2D. So one of the easiest way to define. And then you've got to talk about, because it's just a space, so there's not much to do with it otherwise. So you introduce the shift operator on H2D as the standard multiplication by Z operator. So this is defined in this way. So we'll talk about MZI even in several variables. It will be defined in a similar way by the coordinate functions. Couple of notes. So this S stands for the unilateral shift on L to Z plus. So you can realize this MZ on H2D by S on L to Z plus. However, the difference here is you can talk about analytic thing here, which you, in principle, you can't in the left side. So all the analytic tools appears here, which is not so the case here. Second important thing is the commutator. The commutator of MZ is precisely the H infinity function in this sense. So it's just M of phi, M sub phi, where phi is in H infinity, M sub phi is the multiplication operator with symbol phi. So you can say a Toeplitz operator. I'm just using the notation here. Another aspect is that H2 is a reproducing kernel Hilbert space corresponding to Szego kernels. This is the definition of Szego kernel. And fourth important point is plenty of eigenvector. In other words, M phi star S dot omega equals to phi omega bar S dot omega. So these are all the eigenvectors for any H infinity function phi. So these are the key aspects of the Hardy space. And here is the commutant lifting theorem. So suppose Q1 and Q2 are MZ star invariant closed subspaces of the Hardy space. And suppose X is a bounded linear operator from Q1 to Q2, and it's a contraction. And assume X intertwines the compression of MZ here and the compression of MZ here. If that happens, of course, X is the contraction, then there exists a Schur function phi such that X is the compression of M phi on, so restricted on phi1 and projected, sorry, Q1 and projected back on Q2. So a better way to explain is the following commutative diagram. So you have Q1 and Q2, those are shift star invariant subspaces, and you have X which intertwine the compression, what we can also say as a module operator. And in that case, you can lift this X without increasing the norm to the full space. It's slightly misleading. It doesn't really say that because these are treated as spaces, so slightly misleading. But I hope you understand this is the real thing. I see the clock. Okay. So Sarason's commutant lifting yields a simple and elegant proof of the interpolation theorem, and I like to give you the idea. As I said, I don't know the range of the audience, and the reason is that once you have the lifting, then you have the interpolation free, essentially. So I just give you that, and in future I will not do this part again. So the easy deduction, suppose you have the function phi, which is the solution of the problem. That means phi zi equals to wi for some phi in SD. So you know that m phi is less than equals to 1 because it's a sure function. And if you use that and use this property, the eigenvector property, you can easily prove that the Pick matrix is positive. So that's the easy deduction. The not so easy direction is the other way around. So you start with the positivity of the Pick matrix and you want to get a sure function which does this job. And you proceed as follows. So you consider the NZ star invariant finite dimension subspace Q, take the span of S of Zi. Zi are given nodes there. And then it's a finite dimensional subspace, and then you define X from Q to Q by this obvious way. And then the positivity of the Pick matrix will ensure that your X is a contraction. And by construction, you can easily prove that X star, X star, the completion of NZ, well, X star commutes with your completion, and then just use the Sarason's commutant lifting theorem to get the solution. So this is the way usually one get the proof of Nevanlinna-Pick interpolation. So in other words, if you have the lifting, then this comes automatically. And this strategy works pretty same in all other applications as well. And interconnections, commutant lifting theorem, you can, these are all related to each other one way or other. So one is the commutant lifting theorem. Second, of course, we talked about Nevanlinna-Pick interpolation. Third idea is the dilation theory. Fourth idea is fundamental inequality and invariance of spaces, as well as Toeplitz corona, if not corona theorem, etc. Corona also, in a sense, related, but not directly at all, not directly as the way it happens in Toeplitz corona. There is a groundwork to get into our business. Of course, it's defined, but for the sake of completeness, the Drury-Arveson space H2n is a reproducing kernel Hilbert space corresponding to the kernel K1z omega equals 1 minus just the inner product of the Euclidean ball or Euclidean space of z and omega, as long as your z omega belongs to Bn. Second thing on this particular space, and that's the point, that you can talk about the multiplication operators mz1 up to mzn, you're in n variable, and that gives you a row construction on H2n. So this is the definition of row construction, and certainly you are looking into it in Michael's lecture. All right, so here is the unification and some more example. So we consider a kernel K from Bn cross Bn to C, and which is analytic in the first variable. And if this kernel factors as K1 times K tilde, where K1 is the Drury-Arveson kernel, what you know as a complete Nevanlinna-Pick kernel, example of that. So if K factors as K1 times K tilde and K1 is a Drury-Arveson kernel, then you call this kernel as a regular kernel. Only assumption is that you assume Z is analytic in Z1, Z2, Zn. So it's analytic in the first variables here. That's the definition of regular kernel. And the corresponding scalar value reproducing kernel Hilbert space, whatever you get, is known as, we call them as a regular reproducing kernel Hilbert space. So the idea of this regularness, or whatever you want to say, is nothing but to ensure that the multiplication by Z1, Z2, Zn on HK also defines a commuting row construction. Of course, they're commuting. So it makes sure that your MZI are bounded, and it gives you a row construction, example of row construction, for instance. This idea was there, but I think it was also clarified in a different way from module point of view in one of my paper with Douglas and Misra back in 2012. So if you have a regular reproducing kernel Hilbert space, then the tuple, n tuple of the multiplication operator gives you a row construction. And this gives you a list of examples. So you consider lambda is larger than 1, a real number, and you define k lambda z omega as 1 minus inner product of z omega raised minus lambda. And in this case, the HK corresponding reproducing kernel will be a regular reproducing kernel Hilbert space. And if you consider lambda to be n or n plus 1 or n plus 1 plus alpha, then you are going to get the Hardy, the Bergman, Weitre-Bergman space, etc. Now, vector valued spaces. So if E is a Hilbert space and K is a regular kernel, then you just take the tensor product, and we still say this is also a regular reproducing kernel Hilbert space. However, it is a vector valued, but we'll call this also regular space. Now the notion of dilation. By the way, a lot going on from the Hilbert model point of view, which I'll not perhaps talk about, but it's perhaps easier to see these things from model point of view. Again, except one occasion, I will not perhaps do that. So it's the definition of dilation. So suppose you have a n tuple of commuting operators on some Hilbert space H, and you say that this tuple T dilates to NZ1 tensor identity up to NZN tensor identity on H2N tensor Easter if there exists an isometry pi from H to H2N tensor Easter. So H2N is the Drury-Arveson space over the ball Bn, such that pi of Ti star equals to MZI star pi. So often we say that this pi is a dilation of T. We'll not perhaps talk about, we'll not refer Easter, but it's there. So if you consider pi star, for instance, so pi star will be a map from here to here. So pi star will commute with your, intertwine your Ti and NZI. So from that point of view, pi star is a module. Okay, so it's a co-module map. So dilation is nothing but co-module map. But as well as it's an isometry. So from now on, wherever you will see HK, you assume it is a regular reproducing kernel Hilbert space. So this is our assumption. And here is the dilation theorem. Of course, there are many dilations. I mean, in several variables, perhaps it goes back to Lubin, one of the work, and first volume in GOT, it appeared. Shield, maybe Shield and Lubin, I forgot. But from our context, from the point of our context it is this. So you look at you take a regular reproducing kernel Hilbert space. That means the kernel factors with the Drury-Arveson times another positive definite, and you look at the tuple NZ1 up to NZN with the tensor product. Then that get dilates to H2N tensor Easter for some Hilbert space Easter. So in other words, already we pointed out that in regular space, the multiplication gives you a row construction. In a sense, you can prove also it's a pure row construction, and the dilation essentially follows. However, from the reproducing kernel point of view, it is a little more geometric as well as analytic, and you can get a slightly different proof, and that's the viewpoint of one of my paper, as well as the view of Athavale back in 1980, late 80s, I guess. He was motivated by that. So more specifically, if you want to unfold this says that if you have a regular space HK tensor E, then there exists a Hilbert space Easter and an isometry pi k from HK to HK tensor E to H2N tensor Easter, such that pi k intertwines the backward shift on this space as well as this space. Okay, so this MZI you should understand from the context where it is acting. So for instance, in this case, this MZI is acting here, and this NZI is acting over here. Here's a quick definition of multipliers. I'm specialized on a regular space. It works in general reproducing kernel space as well. So given two regular spaces, HK1 tensor E1 and HK2 tensor E2, you consider a function phi from Bn to B of E1, E2, and you call it a multiplier from this space to that space, if if phi takes HK1 tensor E1 to HK2 tensor E2. So that's the definition of multiplier. And once you have multiplier, you can prove that it gives you a boundary linear map from this space to that this space. And in that case, you can talk about the multiplication operator. So this m sub phi f equals to phi f will be a boundary linear operator. That's a notation. And so the set of all multiplier spaces, the set of all multipliers will be denoted by m of HK1 tensor E1 up to HK2 tensor E2. And this is useful. So and perhaps known to expert, but if you want a shorter proof, perhaps you want to look at it. It's one of my papers in 2016. So suppose you take a suppose X is a boundary linear map from H to N. So now see the difference. I'm keeping H to N in the left and HK on the right. So I cannot take HK on the left. Okay, so there is a problem otherwise. And so X is a boundary linear map, and assume that X intertwines your multiplication here and the multiplication there. And if that does, then your X is going to be a m phi for some phi in the multiplier space, and the converse side is easy. As I said, it perhaps gives you a slightly easier proof, even in one variable, even in the setting of H infinity of D. The idea is simple. So you just, instead of this, you take the conjugate and you get this, and then apply both sides with the eigenvector. And once you do that, use the property on the left side, H2N space. The intersection of the kernel of nzi minus omega I star is nothing but it's just one dimension generated by the eigenvector k1 at omega. So if you use that, and you can get a very quick proof of this fact. So you take all the multipliers of norm less than equals to 1, and we denote it by m sub 1. That's the notation. Now, commutant lifting theorem on the Drury-Arveson space. So first, here is the only occasion I talk about module, but because it saves some time. A closed subspace Q of H2 HK tensor E, again it's a regular space, is said to be a quotient module if it is invariant under the backward shift. In other words, MZI tensor identity star Q goes back to Q for all I. So it's just a backward shift invariance spaces. Okay. And this is the CLT, commutant lifting theorem, in the setting of the Drury-Arveson space. So you take a pair of quotient module from H2N tensor E1, and the other one is in H2N tensor E2. And you take a contraction from Q1 to Q2, and assume that X intertwines the compression of MZI here and the compression of MZI on the right side. If that happens, then you are going to get a multiplier phi of norm less than equals to 1. Here it is 1 here, right? Such that the compression of M phi is going to be your X. And so this goes to Ambrosi, Timotin, and I think the first time it was observed by Bolt, Trent, and Winnicott. And you use the realization formula, etc., to prove this. Again, Agler's idea also comes into the picture. So from this point of view, I recommend also to see the paper by Davidson and Lay, which appeared in 2010. And they prove the commutant lifting in a different way. I think they use the idea of, I think the commutant lifting non-commutative setting of Popescu. Yeah, so they use the Popescu's commutant lifting theorem to prove the commutant lifting in the setting of row contraction in full generality. It did not be a subspace of H2N tensor U1. There could be a isometric part as well, spherical isometric part. Now, as I said, I'm going to touch Agler because, of course, we're not going to do this with bidisc setting or quality setting, but I think it's important to touch Agler's idea. So here is a thing. So again, you start with P points from the bidisc and P points from the disk. And this says there exists a Schur function phi, two variable, such that it interpolates, in other words, phi of alpha I beta I equals to omega I for all I, if and only if there exist positive p by p matrices, gamma and delta, such that 1 minus omega I bar omega j equals 1 minus alpha I bar alpha j gamma ij plus 1 minus beta I bar beta j delta ij, and this should be true for all ij from 1 to p. I think it's a very remarkable result. Here is one note. He used again the realization technique and all that. So if you are looking at the polities, even for any n, not only 2, so this interpolation and lifting, this is really another story, and it comes with different kinds of challenges and surprises. I might want to say it is for us more challenging than the ball. However, it should not be said that more challenging, because it depends on your perspective. For instance, if you look at the recent paper by Kosinski and Zwanek on Nevanlinna-Pick interpolation problem in the ball, you'll see if you ask the right question, the answer could be even more, it would be challenging as well as surprising. And again, from this point of view, interpolation and lifting on the bidisc setting, etc., I recommend another paper by John, which appeared in 2012, and the title is "The Shining a Hilbertian Lamp on the Bidisc." It's a very interesting title. So is on today's agenda, I think I have 24 minutes. All right. So dilations and a variation of the H2n commutant lifting theorem. So we'll just use the H2n commutant lifting theorem and slightly change our view to the lifting problem. And here is the result. So suppose T and T hat are commuting tuples on H and H hat respectively, and assume X is a contraction from H to H hat, and X intertwines your Ti and Ti hat for all I. If all this thing happens, then also you assume, suppose phi from H to H2n tensor E and pi hat H hat to H2n tensor E hat are dilations of T and T hat respectively. So you pick a pair of dilations of H and H hat. Well, you assume they're row contraction. In fact, this will force them to be row contractions. If you do that, then there exists a multiplier phi such that your X is pi hat star m phi pi. Now this looks a little technical, but now you see, if once I show you the diagram from module point of view, it's very easy. So I'm saying the proof, we need to change the following commutative diagram, and here is the diagram. Look, your X is given from H to H hat, and pi hat is a dilation of H hat. So there T hat is attached, T hat is attached with H hat, and T is attached with H, and pi is a dilation of H. That means pi is a dilation of T. And your X intertwines your Ti from here and Ti on here. If you do that, then you are going to lift this thing to m phi from H2n tensor E to H2n tensor E hat, the dilation spaces, such that your X is such that this diagram commutes. That's all. Simple. So this diagram itself tells you how the proof should be. So you go as follows. So you consider the quotient modules Q and Q hat. So just take the range of pi hat and range of pi. So that's your Q and Q hat. So now you are here and you're here, right? And then you look at your X tilde, just go to this Q2 Q hat space, let's say. So you define X tilde accordingly. Once you define this, then you have to do some computation, and that would tell you that X tilde is indeed a map from Q to Q hat. And not only that, X tilde intertwines the compression here and the compression here, right? And that's the time you apply the commutant lifting theorem on the H2n. So you do that, and your X tilde becomes the compression of m phi for some multiplier phi on restricted Q and projected back on Q hat. And again, you play with the projection and inclusion, so on and so forth. And with some easy computation, you end up proving that this diagram indeed commute. And that's the place you use the commutant lifting theorem. Before going to our commutant lifting theorem, I just introduce one more definition. So suppose Q is a quotient module. One more time, quotient module means the backward shift invariance subspaces, okay? And then you take an isometry pi from Q to H to N tensor E star, need not be this E, some other E star. Then you say that this isometry is a dilation of Q if pi is a dilation of the compression. That means you look at the compression, the interpol here over this Q, and then you seek a dilation, isometric dilation. If you can find one, then that's going to be your dilation of the quotient module Q, right? And here is the lemma. Suppose Q is a quotient module and pi is a dilation of this space, HK tensor E. If that is the case, then pi Q, which is pi composed with the inclusion map, is going to be a dilation of Q. So one more time, it's very easy. You see the diagram. So here is the picture. So Q is a quotient module here. So you can talk about the injection, and then you have a dilation, isometric dilation of this regular space to the Drury-Arveson space. You take that. Well, that's given. So pi is given, and what you do, you just take the composition, and that's going to be your isometry dilation because the inclusion is isometry and it's a co-module map. That proves the result. So now the CLT in our setting. Okay, so you start with again two Hilbert spaces E1 and E2. Take a quotient module Q1 of the Drury-Arveson part and take the quotient module of the regular space. And suppose X is a bounded linear map from Q1 to Q2. It's a contraction, and again, like H2N case or like Sarason, assume your X intertwines the compression of the shift operator. So that's here. It's true for all I. So these are all assumptions. If that is the case, then there exists a multiplier phi from H2N tensor E1 to HK tensor E2, such that your X is the compression of N phi on Q1 and compression in this sense, so restricted on Q1 and projected back on Q2. This is precisely the lifting of Sarason in the setting of left space, Drury-Arveson, and the right space as the regular space. Here also the proof can be better explained if I show you diagram, but let me start, let me give you some idea of the proof. It's not that difficult once you see it that way. So clearly you look at the first, you look at Q1, so you look at the inclusion, and that's going to be a dilation of Q1, as I said already. And then look at your HK, the regular space, and you know it is already assured that there is an isometric dilation. So consider pi sub k as the dilation of HK. And yeah, HK tensor E2. Now just the previous result about dilation of quotients. So you take the composition here, and then you're going to get a dilation of Q2, right? And then you are in this picture. So Q1 and Q2 are given, X is given, this intertwines the corresponding compression, and you have the dilation here, which is the inclusion, and here is the dilation which is assured, right, by the previous theorem. And then our previous observation, which is the CLT version, the dilation version of CLT, gives you an existence of phi1, and that completes this diagram. Once it is done, then you are going to have X as pi star Q2 M phi1 I of Q1. As I said, the diagram commutes for some phi1. And that tells you your X is, so just unfold the definition of pi star Q2 and you get that. And you focus on this part, pi k star M phi1. And then you look at pi k star mp1, which is a map from h2n to hk with corresponding coefficient spaces. And then you realize that it intertwines the shift. And if it intertwines the shift, then it is going to be a multiplier. And again, some maybe routine work would really would give you that your x is nothing but the m phi restricted on q1 and projected back on q2. In fact, the entire proof is hidden in this diagram, and this is essentially the picture. So here is your x, and here is you take the inclusion map. I have just rotated the diagram a little bit, 90 degree perhaps, anti-clockwise. And here you have the inclusion, and then you get this pi of q2 in this way, and from there you get mp1, and once you get mp1, you take mp1 pi k star, and that gives you your m phi, and that makes this diagram commute. So this is all about the proof, more or less. I have 20 minutes or 10 minutes or 10, 20, right? 15 minutes. Okay. So here is a result, which is factorization. So suppose again, HK is a HK tilde, I guess. I'm sorry. So K is a regular kernel. Remember, K factors is K1 times K tilde. So assume your this HK tilde is the reproducing kernel Hilbert space corresponding to K tilde. And then you just take a coefficient Hilbert space E. If you have that, then the result says then there exists a quasi-symmetric multiplier psi k from H to N, and this you treat as a coefficient space. So H to N tensor a coefficient space to HK tensor E, such that your kernel K has this representation. So KZW times one identity on E. So that's the kernel function for HK space, equals to psi k z psi k w star over 1 minus z, inner product of z and omega. Essentially, you have to do this. You have to play with the evaluation map. Your k is going to be k1 times the evaluation map for the hk tilde. So you take k tilde as evaluation z composed with the evaluation omega star, and essentially that's your psi k z psi k w star, psi k omega star. You have to do some work, so you have to do some dilation theoretic work and so on, and bit easily you can get this equality. So in a sense, you can extract a map psi k between these multipliers, in between these spaces. So it is going to be a quasi-symmetric multiplier. Now, to understand this construction, I just give you an example because that's more common rather. So you take all the Bergman space, weighted Bergman space, or the Hardy kernel, etc. So in this case, your Km is 1 minus inner product of z omega raised minus m. So you take m larger than 1. In that case, your k tilde is going to be 1 degree down. So it is going to be Km minus 1 z omega. And in that case, you can prove, and it's also in the literature, even before our paper, I'll talk about perhaps. So your quasi-symmetric multiplier will be defined in this way. So psi km omega star, that's the previous this psi k here. So this is going to be given by this star omega star eta is going to be km minus 1. So it's just the evaluation map tensored with eta for all z and omega in Bn, and eta is in E. So this is one kind of a concrete example of the situation. Now here is the second factorization result. So you have Hilbert spaces E1 and E2, and consider an analytic function BE1 E2 valued analytic function. So you stay on the previous setting. That means you have the existence of psi k already. From that point of view, I'm talking about. In that setting, the following conditions are equivalent. So you take arbitrary multiplier theta from H2n tensor E1 to HK tensor E2, That's going to happen if and only if you are going to find a better, in a sense, better multiplier, in a sense, multiplier from the Drury-Arveson to Drury-Arveson itself, such that your theta factors through your psi k. Okay. And this result from the scalar point of view is due to Ball and Bolotnikov in 2017 paper, and then also Aliman, Hertz, McCarthy, and Richter got it in the general case, but still scalar value in 2019 paper. This goes quite nicely again through the diagram. So here is the picture. You have H2n to Hk, and you have a multiplier from here to here. Already you know from this in this picture, you are going to get a kind of a canonical multiplier psi k from here to here. The previous result says, given this picture, so you are going to get another multiplier theta tilde from here to here, such that this diagram commute. Now, as I said, if you have commutant lifting, then you can have the interpolation more or less free. So I'm not going to talk about the proof, as the proof goes very similarly, like one variable. We'll talk about the result here only. So here is the notation: B of 1, E1, E2 is the set of all operator from E1 to E2 whose norm is strictly less than 1. And the Nevanlinna-Pick interpolation problem, as you can state now, given M nodes Z1 up to Zm in Bm, and omega Wi operator from E1 to E2, but strict construction. The problem is to find necessary and sufficient conditions for the existence of a multiplier phi from multiplier phi of norm less than equals to 1. That's the one here. From H2n tensor E1 to HK tensor E2, such that phi Zi equals to Wi for all I. That's the question. That's the problem. And here you can state the interpolation problem in this setting. So here is again, so you start with Zi in Bn and Wi in B1 of E1, E2. Then the following are equivalent. There exists a multiplier phi of norm less than equals to 1 from H2n tensor E1 to HK tensor E2, such that you can do this interpolation if and only if this inner product of this regular kernel, remember, so this is the regular kernel, okay, and it's a vector valued in this case, sorry, operator valued. So operator valued in this case is the identity minus this is the operator Wi Wj star, and this is the scalar, the kernel of the Drury-Arveson kernel, rather, and you take this inner product. Essentially, this is positive definite, okay, and that's what it is written. So this guy is going to be positive definite, and if you write it in terms of the inner product, that's what it comes out. And third condition is that, so remember the factorization. So if you are going to get a phi, then you know this phi is going to get factored through your psi k, and essentially it's a restatement of that. So you are going to get a phi tilde, which is, let's say, nice multiplier from H2n to H2n itself, such that psi k, the canonical, times phi tilde, nice one, at Zi is going to be Wi. That's the interpolation in this setting. All right, so in the case of scalar valued multipliers, again, this 1 and 2 is due to Aliman, Hertz, McCarthy, and Richter in their 2019 paper. And if you go back to n equals to 1 case, that means in one variable, and still in the Bergman or weighted Bergman case, etc., then this equivalence is due to Ball and Bolotnikov in their 2017 paper. And just for example, to understand this more for a concrete case, so consider this HM, where HM is the regular reproducing kernel corresponding to KMZ omega is just this raise minus m. If you are in this setting, in this case, then the previous result, the interpolation result, you can state it in slightly better way. So here you go. Given distinct m points Ci in Bn and m points omega I in D, there exists a multiplier phi of norm less than equals to 1, a multiplier norm less than equals to 1, such that phi zi takes you to omega I if and only if this m by n matrix is positive definite. So now you see this is the, let's say this is the Bergman kernel here. This is the Drury-Arveson kernel, and omega I, omega j bar appears here. This is a scalar. And of course, if you are in the Drury-Arveson space, n equals to 1, you get back the known positivity assumption. And this is all about interpolation from the concrete analytic space point of view. And I like to conclude with one note that so this result of Ball and Bolotnikov is perhaps fast along this line. However, there are other papers. So one is the Shimorin's paper, which talks about commutant lifting from reproducing kernel point of view. I think it appeared around 2005, and I believe he was further motivated by another classic paper by Trail and Volberg, 1990 plus or something like that. So these two works also should be watched by. So one is Shimorin and another one is Trail and Volberg. Thanks for your attention.
Thank you indeed, Jaydeb. Let's thank the speaker first. Yes. Questions and comments for the speaker? If there is no question or comments, let's thank him again.
Thank you.
Thank you indeed. And we resume in about 14 minutes.